Now, please allow me to introduce you our guest speaker this morning, Peter Nimrichter. Peter leads Boots Canadian Climate Resilience and Sustainability Services Program. Peter has been involved in climate change themed projects for about 15 years and has a background in vulnerability assessment, adaptation planning, resilience engineering, and life cycle roadmap development in the municipal, water resources, transportation, energy, and mining sectors. As well, his water resources career has spanned 30 plus years and has focused on flood risk assessment and mitigation planning and urban stormwater management. Peter is a strong advocate of advancing better understanding of our vulnerabilities and future uncertainties as a path to better, more informed decision making and policy development by providing a basis for establishing priorities that increase confidence related to system planning and enhance infrastructure management. Please welcome Peter with a round of applause.
There we go. Oh,
Yeah, that's good. Is this your next presentation?
that's the second one.
Okay, I'm not gonna change it.
There we go.
Very good, Anya. That's
Thank
your
you.
pointer.
Thank you very much and good morning. Just to give you a little bit more background, my longer career, as Shabnam indicated, is as a water resources engineer, focusing on flood risk and computational methods to help water resources engineers in the development of flood risk assessments, floodplain mapping, and such. And I think that was a very good place for me to be, and my beginnings in climate change work happened very coincidentally sitting across a lunchroom table from a gentleman who came to our firm and brought a project with him looking at adaptation options in the coastal zone of the Great Lakes, and he was looking for a project coordinator. There was a bunch of water overtones, of course, so I kind of raised my hand and said, sure, that sounds great. And it was a super interesting project and kind of gave me that fire to continue looking for those kinds of projects, and eventually you become the guy in a company that has the longest resume doing this kind of thing. So I've had the opportunity of being involved in a number of really interesting projects in climate change, in water resources, bringing those two things together. So Ali was kind enough to ask me to present this morning on a case study on a floodplain mapping assignment we're doing now that Hassine mentioned this morning on the Humber River watershed on the west side of Newfoundland. And I'm going to kind of introduce a little bit of an overlap with what Hassine presented this morning, but go maybe where Hassine was focused a little bit more on policy. We'll delve a little bit more into the technical details about how we're integrating this information into our modeling and mapping. So I just want to thank Ali and Hassine for inviting me, and of course Mohammed and Shabnam and Rob. I don't see Rob. Rob's here somewhere. But these are highly technical assignments. They have a lot of moving pieces. And just in terms of our internal project team, we have senior review, we have modeling advisors. Luckily, we're a big company. And just show of hands, who knows wood? Oh, good. I was at a conference out in BC about 3 weeks ago, and in a room about 3 times the size, one person held their hand up. So that was a fun room to be in. But there's lots of different pieces to these. We have a lot of great contractors that are working with us on various different pieces, particularly on the ice side, which is a unique specialization that doesn't have a lot of people operating in that space in Canada. So we're very fortunate to have Dr. Carl Erich Lindenschmidt and Secor on our team helping us with those aspects. So there's I mentioned this morning, we're pretty much the choir in the room here. It'd be nice sometimes at these kind of events to have people in the room that are a little bit on the other side of the fence of the climate change topic. But we know that we have existing vulnerabilities. We know the changing nature of climate that's projected through the global climate models, that our vulnerabilities or existing vulnerabilities are just going to get exacerbated. And just kind of an overview of what I'm going to talk about, history of floodplain mapping in Newfoundland and Labrador. You'll see some slides that are identical, if not virtually identical, to what Hassine had this morning in his presentation. The requirement for new pieces to be added to those floodplain mapping assignments, the recognition that that rainfall patterns are changing, integrating climate change, standardization of data, and a little bit of commentary on how the rest of Canada is really lagging behind Newfoundland in this topic. How the future floodplain maps are used, and that's really going to speak to the land use policy that Hassine touched on, and then the Humber River case. And in items 1 through 6, talking about one of the first floodplain mapping assignment we did with WRMD for the Corner Brook Stream, Petries Brook, and Petty Harbor River on the island. So this, I'm sure everybody's somewhat familiar with, the evolution of floodplain mapping programs in Newfoundland, the FDRP program, the interim program that also facilitated a number of floodplain mapping assignments, and a number of areas mapped through those programs on the island. But even though those programs ceased, of course, it still rains, it still floods. So there's got to be a recognition that some technical work has to be done in these areas to help our communities understand what their risks are. And certainly the Catalyst event in 2005 in Stephenville prompted a review of that, and this Hassine spoke about this morning, the Environment and Climate Change Canada data over not a great deal of time, 20-odd years, showing pretty positive and substantial increases in rainfall. And the basic requirements of a floodplain mapping assignment, you have your background review, you pick your models, in this case, for the work that we're doing in Newfoundland and Labrador is based on U.S. Army Corps of Engineers software, the HMS system, which used to be HEC-1, and the HEC-RAS system, which used to be HEC-2. You do work out in the field, you kind of try to understand what your flow regulation regime is, what your dams are doing in your watersheds if you have any. You do LiDAR and aerial photo data collection, which for us, we were just talking this morning, has been a struggle for our programs that started last year, because last year in the fall was so crappy we couldn't get planes up in the air. Land cover inventories, so assessing using satellite imagery, what's the cover on the ground, and model development, inundation maps, and then this new piece, the climate change analysis. And there's this kind of looping exercise that happens with the climate change analysis and understanding, the sensitivity of the watershed, and how that flow regime is changing, and then how that changes or how that morphs or translates into how much water is coming off a particular watershed in terms of hydrology, and then converting that amount of water into how high the water levels get in your particular riverine system. So when we did our first project, and this started in the 2011-2012 timeframe, there were a variety of different climate change analyses that were available to us. The Gary Lines information that was done more on an Atlantic region. There was a Joel Finnis work from 2013 that we integrated into the project. And at that time, we were, for that project, also requested to do our own independent forward projections of IDF, and that was based on then the CMIP3 multi-model data set, and we were able to generate through that data set and statistical analysis about 48 variations of future IDF relationships for the gauge network that we were looking at. So through that exercise, this just kind of reinforces what Hassine touched on this morning. Using the Environment Canada 1996 IDF relationship for St. John's Airport as a base, when we added in some of the interim rainfall results from various gauges, there was a 24% increase on the 100-year 24-hour storm. And then we see the requirements for 2020, 2050, and 2080. There was also a requirement in that initial project to look at those 3 future timeframes. So we see, going out to 2080, and of course the error bars in this are pretty big, but we see almost a 50% increase in potential rainfall. Now, the one thing in the Joel Finnis information from 2013 is it provided discrete rainfall depths for the 6-hour, the 12-hour, and the 24-hour storms, which allows you to, in terms of your hydrologic modeling, allows you to use something like any of the predefined distributions for rainfall, Soil Conservation Service distribution, Watts distribution, Chicago distribution, in order to develop your rainfall hyetograph, so distribute that total rainfall depth to create a 5, 10, 15-minute time series of data that can actually drive your hydrologic model. But with the work that the independent statistical analysis that we were doing, it allows you to project out a full IDF spectrum, which is interesting in itself because there are jurisdictions, say in Ontario, currently that integrate climate change into their infrastructure assessments by simply shifting their current IDFs by, say, 20%, 15%, just a kind of an arbitrary number. But this work that we did early on here clearly showed that the percentage difference in the IDF spectrum is variable. So you don't get a standard 20% difference across all your durations and all your return periods. So having this full spectrum IDF as a future representation allows you to integrate that information directly, and there's a method called the alternating block method that allows you to take all those information off the IDF and actually build your hyetograph that drives your hydrologic model. So that was huge. So in terms of hydrology and hydraulics, again, Ali and group have decided that non-proprietary software is the way to go. So all the information, all the software that we're using for these programs come from the U.S. Army Corps of Engineers. They're free to download and install. They come with great documentation. There's a massively large user community out there. So you'd be hard-pressed to find somebody who doesn't, as a water resource engineer or water resources modeler, doesn't know these programs. Interesting enough, there is a move in the software industry, in the water resources software industry, to suggest that more expensive software gets you better results. And we have a number of municipalities in Ontario that have moved to software platforms that cost upwards of $100,000. We're kind of the counter to that. There's lots of software out there that will support your decision making that doesn't need to cost you that amount of money. So in terms of integrating climate change, and Hassine again touched on this morning, there's all kinds of data products that are available through these projects. The typical floodplain map, whether it's on a topographic background or an aerial background, and aerials I've always found in public information centers are good. People always manage to find their houses a lot quicker using an aerial photo than a topographic map, and they're always interested to see what's happening at their particular property. We have the depth maps, which help with first responders, and I didn't put a velocity map up here, but those two, or the risk maps, those number of things in combination not only help us regulate land use and development, they also help our first responders, and they also help us in future planning. And these, this is Petty Harbor, flood map from Petty Harbor, but we were also required to build floodplain maps for those 3 future periods. So that becomes really interesting because you start to see, at least in this circumstance, we had increasing rainfall, so you see expanding floodplains. And this now allows you to quantify some of those differences. So between, compared back to using the 1996 IDF relationship and looking at the floodplain that would be generated from that, and updating it to the current circumstance, and then looking at our future periods, we see, as almost a doubling or a 10% increase potentially in flooded lands moving into the future. So that helps a community to recognize that its flood risk is potentially increasing as we move forward in time. And Scene also showed this particular image, or one similar to it. But we see through looking at our structures and bridges and culverts as such are where kind of our communities really directly interface with watercourses. And a lot of watercourses, if they're undersized, are usually one of the first casualties of large rainfalls and flood events. But this starts to provide communities with some information around when they need to make decisions. So if we see changes, and if I recall, the blues are where, or the blue highlighted fields are where the water depth is between the soffits, so the top of the opening and the top of the roadway, and the reds are where we're getting overtopping of the roadway in a particular flood. So here it's this particular page is somewhat binary in that you're either you have a free surface under the bridge, you have it in that kind of submerged zone, or you have overtopping of the bridge. There are only a few circumstances where you're getting this change. And if we look particularly at the main road, circular culvert on the Dirty Bridge River, in the middle of the sheet, you see this transition between submergence and overtopping. So, and that is into kind of the 2020 period, which is almost upon us now. But that provides, at the time, a mechanism for communities to say, we should maybe plan for either special emergency planning around this particular structure, or perhaps replacement of that structure and upgrading of the opening to accommodate a larger flow. And we found that generally in our climate change work, not all decisions have to be made right now in terms of capital works, because climate change is very nonlinear. A lot of these decisions can be pushed off into the future as long as you have a plan for them and have either plan for budget or plan for land requirements to allow you to make these changes when they're actually necessary. So the original Finniss work that we were using in the Corner Brook Petty Harbor study came from Joel Finniss here at MUNS in 2013. And in addition to the IDF relationships that we used in our project, there's a whole host of other information. And again, Newfoundland is way ahead of the curve on this. These are provincially, Ali, correct me if I'm wrong, provincially approved data sets for engineering and design use across the province. I'm not aware of any other province that has this kind of information. I should say, has this kind of information, but it's not provincially approved. So I think in here I've got an example from Ontario. But there's a variety of different information beyond just what we would use for floodplain mapping that will help with changing HVAC systems, changing pluvial flooding, so overland flooding, a variety of different things. And similarly, the sea level rise, projections that are still current. Now, in terms of standardization, another tool that you have available to you is the IDFCC tool from University of Western Ontario. We use this a great deal in other provinces because this is a tool that goes right across Canada and will allow you to generate an IDF relationship for your specified time period in the future at any Environment Canada and Climate Change, or any Environment and Climate Change Canada station. But they've recently also added tools, so if you're in an area that you need to do some design, you need an IDF relationship, but there is no closed gauge, you can generate an IDF relationship for your specific location in space. And I'm not one to fully understand all the mathematics behind that, but they use some aggregation of information from adjacent gauges to essentially interpolate an IDF relationship at the point of space that you've defined. And that can be we find it very handy, particularly in Northern Ontario, where the gauging network is pretty sparse, and I'm sure there are areas in Newfoundland that would have that same circumstance. So the climate change data that I think Hassine pointed to this again this morning, all the information is available. As he said, WRMD and the department is totally transparent about all the data that they have. And this is wonderful because in other areas of the country, it's not as easy. Hassine went over this morning. I would just point out that where I live in Ontario, Ontario hasn't moved in this direction. I think we're still stuck with the idea that if we generate maps that represent future possibility of flood risk, that somehow those have to be tied back to whatever land use policy we have right now. And I think Newfoundland made a very wise decision to separate those two things. Because I don't think anyone else in the country has similar land use policies, not that I've seen anyway. Future floodplain maps representation, again, easily accessible, publicly available, makes looking at this information very easy. And from a community planning point of view, again, if you're looking at developing critical infrastructure, hospital, police station, community center, this sort of thing, knowing that areas of your community may in the future be flooded helps with your decision making to keep that infrastructure out of those zones. And there are other provinces have moved similarly, but differently. So in Alberta, some critical infrastructure has to be placed above the 1 in 500 year flood. In Ontario now, where we used to just look at the 100-year and what we term the regional flood, which is a variation of Hurricane Hazel. It happened in 1954. We're now looking at the 350-year flood, and we're developing flood lines for that particular event. So I think Newfoundland, as I've said since we started doing work with Ali and his group, is way ahead of the curve. The rest of the country is catching up, and every opportunity I have to point people in the rest of the country to speak with Ali and his group, I make those connections. So the work we're doing right now is on the Humber River and on the west side of the island, and it focuses, even though we're doing floodplain mapping along the entire reach, which is about 75 linear kilometers of watercourses, there's a particular focus on the communities along the study area, including Deer Lake, Pasadena, Humber Village, Little Rapids, and Steady Brook, and has a number of different watercourses beyond tributaries to the main Humber River included. And the mapping for this area, or parts of this area, does exist, but it is rather old. And there's continued flood risk and consequences of flood risk in the communities along that particular study reach. So this is just an image of where land is disappearing because of erosion and floodwaters and erosive velocities in the community of Deer Lake. So our particular study area, and this is this is just an image of the LiDAR and aerial photography information that we're collecting. I think we're covering about 300 square kilometers. And this is key to a variety of the modeling assessments that we're doing. And up in the community of Reedville, particularly, there's some extra things going on just because of the consequences of a major bend in the river right as it enters into the lake, and some bathymetry work that's happening at kind of the confluence of the lake and the river. There's remote sensing going on. This helps inform our hydrologic modeling. So this is done based on satellite imagery that's collected for the entire watershed. And then this is multispectral satellite imagery that people smarter than me use tools to assess on a grid-by-grid basis what is the underlying land cover. So we have these 8 particular categories that we use that help inform, as I say, help inform our modeling, because each of these classifications has different runoff characteristics. So the model setup, as I said, the LiDAR data has been a challenge. It was supposed to be flown last year, but the weather was so crappy on that part of the island last year that our contractor was not able to get planes up into the air. So they flew the LiDAR this year, but we had to move on with our model development, so we used the Canada Digital Elevation database to inform catchment boundary definition, subcatchment definition, and such. The land cover classification information that we have that was generated, as I mentioned, from the satellite interpretation, as on a 10 by 10 meter grid. We have soils information. We have a variety of background studies, including the old Steady Brook and Deer Lake hydrotechnical reports. And we have information for how the main dam is operated during flood. So we have about 200 subbasins in our model using an SCS curve number. So curve number relates to runoff potential for a particular subcatchment. Unit hydrograph to transform subbasin flow into a hydrograph. And Muskingum-Cunge is just one of the various routing options that you have in the HMS model, and we felt it most appropriate for this particular circumstance. So as I say, we have the land use classification map, we have the soils type map, and these two things brought together help inform quantification of our curve numbers, which are then aerial averaged over a subbasin to generate our watershed response regime. So we have, for meteorological data, we have the 25-year and the 100-year. Unfortunately, we have to translate back to the 20-year to support our floodplain mapping assignment. We have 3 gauges at Daniels Harbor, Deer Lake, and Stephenville. And we're taking the 24-hour design storms and converting them down into 5-minute time series for design storms using the alternating block method, as I mentioned previously. Excuse me. And we're divvying up the areas of our watershed that are influenced by rainfall as represented by these gauges using a Thiessen polygon method, which is just a triangulation method that divvies up the watershed, so you can associate particular subcatchments with particular rainfall stations. flow data that supports our calibration efforts. So in calibration, what we're doing is we're running our model for a known storm event. So and comparing that to recording in the field, or statistical analysis that's done for recording stations in the field. So the one interesting thing is anomalies. So is there a pointer on this? There we go. The software that we're able to use now, you can bring the digital elevation model, so the topography information that comes from either your LiDAR or other topographic data sets. You can bring that directly into the HEC HMS system, and there are tools there that help you to automatically delineate your watershed. Now, it's interesting here, on the original data set that we used, doesn't go that far. So we have a variety of representations of the watershed from various information sources. Using the database, the topographic database that we have, it delineates the hard line around. But we have these two areas that are kind of left out on the east side and the north side that we needed to go back and find out why our systems are saying these areas aren't contributing. So there are a variety of different means that we looked at, other databases, other resolutions of topographic information to confirm that the area on the east side was indeed draining to our watershed. The area on the north side is still questionable and something we'll talk about on Thursday. So in the interim, between doing our Corner Brook Petty Harbor study, there was a 2015 update, and Ali, again, correct me if I'm wrong, that was when the decision was made to not do the 3 future time frames, but only focus on 2050. Because that data suggested that, you know, in most areas of the province, 2050 represented a conservative representation of rainfall for kind of the foreseeable future. So even in comparing the 2013 results that Joel generated compared to his 2018 results, and just focusing on 2050, we see, you know, increases. So we've got a different set of data from the IPCC that now aren't based anymore on the SRES, the economic scenarios, but they now have the RCP scenarios. Excuse me. So there's kind of a methodology change in the background. Mathematics have improved. So a variety of different things have changed, and now we're seeing even more substantive projected changes in precipitation for the province. So as I mentioned in the 2013 report, we just had rainfall totals, but now in the 2018 report, we have the full spectrum IDF relationships that really give us an opportunity to look more directly at how rainfall is changing in the future, not just on total, but how the shape of the rainfall hydragraph is changing. So in Ontario, because we don't have provincially approved data sets to use, we have this somewhat of a competition between different data providers, the province being one, that offer up all kinds of options. So we also have, because of a national system, we have the IDFCC tool from the University of Western Ontario. We have the Ontario Climate Change Data Portal, which also offers future IDF representations. And this one is somewhat analogous to what Newfoundland has in terms of it's a gridded system across the entire province. And then, for whatever reason, the Ministry of Transportation in Ontario decided it needed its own tool. And I think the fundamental reasoning was that they needed an IDF generator for areas where there was no gauge. So this particular system predates the IDF CC tool bringing in that functionality. Each of them has the potential to generate a future IDF relationship. And we as engineers in Ontario are challenged because we almost have too many options. And they're all different. And I'll say, as kind of a baseline statement, they're probably all wrong. But hopefully they're at least a little bit close and at least can inform our decision making. So we did as an add-on task to a stormwater master planning exercise with a community in Ontario. They said, we've got all these tools. What rainfall should we be using? What rainfall should we be using to inform our future planning of our drainage systems? So we looked at these and as well Environment and Climate Change Canada data, and we very quickly came up with about 90 different options of rainfall, 90 different definitions of possible future rainfall, just for this one community. So that's a challenge for anybody. I harken back to one of my university courses on retail philosophy. You give people too many choices, they won't choose anything. So helping communities understand what all these variations mean, how they can use them, not necessarily just picking the biggest one, because communities generally don't have enough money to deal with those, but understanding something in the middle and recognizing, and I'm not a legal person by any means, but some of the talks I've heard on the legalese around climate change is decide what you're going to do, make an informed judgment, and carry it forward meaningfully is really what will limit your liability. So you don't have to pick something that's going to save everything. Just pick your appropriate line, what's appropriate for your community, and move that decision making forward. So we also have the sea level rise estimates, which we're using, which Hassine again talked about this morning. On the hydraulic modeling side, as I mentioned, we're using HEC-RAS, the newest version, 5.06, and this continually evolves, and you simply need to go download the new one. Typically, the typical bug fixes, new functionality, a variety of different things, but it's a very stable platform. It has served us as water resources engineers for decades, and I expect it will continue to. There are lots of other options, particularly if you get into more advanced modeling around two-dimensional modeling. But for floodplain mapping, I would say in North America, the Hydrologic Engineering Center software from the U.S. Army Corps of Engineers has been pretty much the mainstay. So for our hydraulic modeling, this is just kind of a floodplain map sheet layout, because when we started into the project, looking at the number of floodplain maps we'd have to develop across all the different flow scenarios, all the different variations of representation of flood data that we're supposed to do, we would have ended up with somewhere around 1,200 map sheets, which we thought was somewhat overwhelming. So working with Ali and his group, there are clearly some areas of the watershed that aren't as developed as others. So we're focusing the more resolute mapping, i.e. the small rectangles in areas where there's more development, and the larger scale sheets in areas that aren't, and we're kind of bringing the product number down a little bit, while still maintaining the development of maps that will help inform development in the study area. So hydraulic modeling will incorporate all the bridges. In our case, I think we have, if I remember correctly, 12 bridges, which isn't bad. We have all the drawings available for those bridges that will help us to code in HEC-RAS the bridge representation. I compare this to work we're doing. We have 2 projects ongoing right now in Ontario with the Toronto Region Conservation Authority, which admittedly is in a much more urbanized area. But these studies, these models have, at last count, about 5,000 sections and about 400 bridges. So a much different kind of circumstance, but the concept in terms of model construct is exactly the same. And this information, again, is akin to the bridge data table that I showed earlier. It's just now we're only looking at the 2050 circumstance. It'll still present that same information and still provide a mechanism for some of that future planning. Now, the new piece, as was mentioned already, is the flood forecasting system. And it's challenging because the core of the system is based, again, on a U.S. Army Corps of Engineers piece of software kind. The RTS system is real-time. Do you remember, Ali, what the S is? Thank you. Real-time simulation. So it allows the integration of your the hydrologic model and the hydraulic model in a seamless framework to generate flood forecasts. And I'd be interested to hear what David's going to talk about on the other forecasting system, which is much more advanced in development. But it also integrates a fully functional front-end meteorological forecasting tool. So all of that is integrated with real-time data, forecast data from Environment and Climate Change Canada, observations in the field, all brought together to inform flood forecast. Similar to what Hassine was talking about, and I'm sure David will speak to also in his talk, the need for river ice forecasting, which is a real issue. And then we have, as part of our tasks, implementation of all the forecasting models, training of staff, building of user guides, and so forth. And as I said, the basic construct is monitoring of weather, bringing all that information in, doing all the data processing through hydrologic and the hydraulic modeling, developing operational forecasts, and if those forecasts suggest that a warning should be disseminated to communities, then tools to do that as well. And pretty close. Thank you very much.
Thank you so much, Peter, for your great presentation. Now we're a bit ahead of time, so we have lots of time for questions. Anyone has any question for Peter? We have mics in the back.
Yes, sir.
Yeah, so you had a hydroelectric development in that case study. I was just wondering if, I guess in your experience, was there ever like a rainfall event that would suggest that a structure like a dike or dam or control structure would fail or overtop? And if so, like how would you handle that?
In the context of our work that's really driving development of floodplain maps, we don't look at the dam safety aspects. That's an entirely different path that Ali can probably comment on, but it's typically done on the private side as opposed to the public side, unless it's a public structure, of course. But sometimes getting information out of dam owners is a real challenge. So we've had instances in other projects where we have needed to bring some pressure to bear to release some information. And sometimes it's under non-disclosure agreement or other special type of sharing, data sharing agreements that allow that information to be passed back and forth.
We have Paula here, who's the dam safety manager. She can answer that question too, add to it.
Just with respect to dam owners, all dams are supposed to, under the Canadian Dam Association dam safety guidelines, they're supposed to have their dams classified in terms of the consequences if the dam fails. And as part of that, dam owners are supposed to develop dam break flood maps to help with that consequence classification. So a lot of the larger dams in the province, they do have, especially where there's populations downstream, they do have that mapping done in the case of a dam failure.
Thank you. Other questions?
Do you know if the IDF CC tool that you presented, do you know if that includes the updated IDF curves that were done by CRA back in 2015?
I think
Or is that just Eastern Canada's latest, not Eastern Canada, sorry, Environment Canada's latest IDF update?
I would have to go back to the tool and actually take a look.
Okay.
But they very clearly document what version of the Environment Climate Change Canada IDFs are kind of used as a base.
Okay.
Hi, two questions for you. You showed an image of eroding banks, and obviously as we get more, as there's more water running through our rivers, we end up in some circumstances where the rivers might actually change course, jump backs, and it would completely change the flood map. Do you look at bank stability or any sorts of studies that might allow communities to predict or understand where they're most vulnerable to that? So that's my first question. And then similarly, I was really pleased to see the ranking of the infrastructure and where the various bottlenecks are. But obviously, as you remove bottlenecks, that can change downstream as well. And have you looked at the impacts of that in terms of helping communities understand the impacts as they start to implement the changes in their infrastructure?
In answer to your first question, erosion and bank stability is not a defined task in the floodplain mapping programs. There's certainly mechanisms to do that, and information that is generated through the floodplain mapping work that Wood and other consultants do for the province in terms of, say, velocity profiles would be very key to understanding what the erodibility is, because typically what is the kind of soil structure of the bank and what kind of velocities are acting on that material would define the erodibility. So the information in part comes out of the floodplain mapping program, but the actual bank stability part is not a defined task. And in terms of moving rivers, agree. If you look paleo-wise at a river, we did such in a floodplain mapping assignment in Ontario. Over tens of thousands of years, it probably moved a couple of kilometers. That kind of movement probably won't happen in our lifetime, but you might experience, say, if you have an oxbow, something breaking through, and absolutely those things will change. Ali and his group are home to all the simulation models that are generated through these projects. So they have the ability either to update them in-house, or if it's something more substantial, to award that out to a consultant. And similarly, if you're changing a bridge structure from one that is undersized to one that is more accommodating, in the hydraulic models, in the manner that we run them to develop the information to support floodplain mapping. They work from downstream to upstream. So if you make a bridge bigger, the influence of that bridge from a storage perspective or that isn't really recognized in that simulation, but it would recognize a change upstream. And again, the WRMRD has all those models, and I'm sure would be in close partnership with a community that's looking to change some of those structures and understand, what other changes might result, as a catalyst to, changing that bridge or that culvert.
Yeah, and I was just going to add, I work with the province, but with the Geological Survey, and we look more at coastal erosion, but we do try to understand the superficial sediments, so whether or not they're sand or silt or clay, when we look at our erosion, because, sand will react very differently than a clay bank in terms of the processes that cause erosion, and also in that case, too, whether or not the sediment is frozen, or whether it's thawed, because all of those factors are pretty important in determining its stability.
So Melanie looks after the coastal erosion program, so they are going to cover this in more detail in the workshop 2 days from now. Just to add to what Peter said, rivers do change. The Stephenville River, the 2005 flood that happened in Stephenville made the river move. And when that happens, we do a new flood risk mapping study. And secondly, one of the reasons why we're making our models publicly available is that if a town finds they're changing a bridge, they can go and model the impact of that. And then in 5 years' time or 10 years' time, when we go back to redo the flood risk study, we'll incorporate all of that. So we do work with the towns on that. Thank you. Any other questions? Sorry, got a bad cough.
I just wanted to add one thing while the mic was changing, which happened way too fast. There was a circumstance in BC, and I don't think we have the same circumstance here in Newfoundland and Labrador. But with climate change, warming temperatures, and receding glaciers, there was a documented instance of researchers going to look at some aquatic habitat on a river, and it was rather remote. They trekked out to the river only to find the river was completely dry, which is completely unheard of. So as they moved back upstream, they realized that the glacier that fed that river had receded far enough that the river completely went in a different direction.
I just have a question about IDF curves and IDF projections. These are, of course, they are estimates of point rainfall. Mm-hmm. Do you have any thoughts about applicability of these estimates and projections on very large watershed areas, depth area adjustments, for example?
It's really hard. I don't know that anybody's really looked at that in any great detail. We generally still struggle as engineers with the broad error bars that even the point rainfall projections have. Even though we tend to forget, even with the published IDF information that we have from Environment Climate Change Canada, it has error bars around it. But in direct answer to your question, no, I don't think a whole lot has been done on that. So in our modeling, we just take it as basically a constant.
Any more questions? Oh, well, thank you.
Thank you very much.
All right, so our next item on our agenda today is a roundtable discussion. So we prepared 2 questions for you, as you see on the screen, and we would like you to, on each table, discuss this between yourself. And you have about 25 minutes to discuss. And one person, a lead on each table, would report back on your answers. So, yeah. it's going to be on Tuesday. And I'm not there.
Can't do that in the rain. What's the time?
All right, if I can have your attention, please. We can perhaps start with that table on the right side. Can I ask your table lead to share your findings with us, please?
Hi, we just have a couple of points. One thing in terms of meeting community needs, we talked about how communities might be looking more for like more comprehensive hazard maps. So things that integrate not only flood mapping, but other hazards like landslides or avalanches or sea level rise, that kind of thing. So they know where they're vulnerable. The other thing we looked at is having a dedicated annual budget for flood risk mapping with the province. So a lot of the times we're just, applying for money from the federal government to see if we can get matching funding provincially. There's no dedicated budget to do flood risk studies that we can rely on. Also looking at incorporating the flood risk mapping into municipal plans so that you can have, I think municipal plans have to be updated every 10 years. So if you could time the flood risk mapping studies so they get done before the municipal plan has to get updated, so they could be kind of more integrated, one learning from the other, I guess. The other thing we talked about was sometimes there's hidden infrastructure, things like septic tanks or oil tanks, not just bridges and culverts. And so these things could cause problems, contamination that isn't really highlighted in your flood risk studies. And having some kind of centralized provincial LiDAR repository would probably be really helpful for everybody.
Thank you. Excellent points. Can we move on to the next table?
Hello. So I've been voluntold. So we have a representative from Bay Bulls with lots of really good insights to municipal issues. And like table one, we talked about erosion and the need to understand how that is affected. We also talked about groundwater and the interaction with groundwater and drinking water sources, and maybe it's related to septic systems as well. The fact that the flood risk system doesn't really address that at this point. And then, of course, the changes in the flood plain with development and filling in bog areas, that kind of thing that has a cumulative effect.
Excellent. Thank you so much. That table.
I've been asked to speak because I know the least about this. We think the key thing that municipalities need is a line on a map that they can look at that says these areas are vulnerable. We also think there's an opportunity to integrate, and Kathleen Perry was here, she works with, oh, there she is. Kathleen works with municipalities Newfoundland and Labrador, and our little company's been doing a lot of asset management planning. We think there's a real opportunity to integrate asset management planning with climate change adaptation and flood risk. We think flood risk is the elephant in the room in terms of climate change in Newfoundland. And if you have the information on topography, on soils, on vegetative cover, identifying levels of vulnerability as part of these studies would be brilliant for those communities. And I guess for communities to understand, this is very complex. And still, if I understand it correctly, the margin of error can be this big. We've got 256 communities in Newfoundland. Is there a way that we can, oh, thank you very much, Kathleen, 276 communities. Is there a way to apply some kind of metric based on observation? The province has a young lady, Jessie, forget her name, but she's awesome. She's going around talking to communities about flood risk and thank you, Kathleen. I got one more. She's with the Conservation Corps, but she's working with municipalities to identify where are your areas of vulnerability, and a lot of it is dealing with water and flood risk. And your idea that was mentioned in the first table of doing your flood risk mapping as part of your municipal plans, which we think is a great idea, but having a map that a municipality can look at to show the line that they shouldn't cross in terms of development, it'd be a great place to start.
Thank you so much. Can we move on to the table in front? Yeah.
Come on, guys. I joined you.
I guess I can.
You can. You go.
Yeah, I guess we first of all we discussed that it's meeting the community meets communities' needs to actually have flood risk mapping. So like others have said, we kind of need to have I guess more funding in place so that communities can do these studies before there's actually a disaster that we have to respond to, or the squeaky wheel getting the grease. So that's one thing. Another thing that there's been discussion at this table, or I guess education on asset management and how like flood risk mapping can be a tool for down the road for asset management and gaining funding and things like that. This could be a parameter, I guess, for that. I don't know if anyone else wants to add anything.
Yeah, we talked about a key driver for communities is the funding, through the climate lens assessment program that both government levels are now requiring. That's an important aspect in asset management for communities.
Thank you. And probably this table in front. You guys, yeah?
Find my, excuse me, I didn't think it was that loud. Okay, answering the first question, we were, wrong page. Asking ourselves if the flood risk mapping meets the community needs, we decided it did. We did find from our own experience that data is sometimes difficult to relate to elected officials and to the general public, and it's already been said, draw a line in the sand. Peter mentioned that. Asim also mentioned the same thing. Being able to draw a line in the sand or on a map to say, this is the point where we think you're going to have a problem, is the only thing that we feel that we can do as far as a community in using the flood modeling that you have in public work. There's a disconnect between what we know and what we can do about it. There's when it comes to land development, the private benefit and the public risk. Those are sorts of things that we struggle with from a planning perspective as far as development goes. What else do we say? Lack of benchmarks and targets. That's where the mapping works out for us, because it gives us a benchmark, it gives us a target, even though there's a liability there, or what's the error margin, which might be wider than what we'd like it to be, but that's as close as what we can even guesstimate. So that gives us a balance. And that personal responsibility, we've talked about how homes get flooded and then get repaired on public money and then flood again. That's something that we probably all run into, or at least seen. That's a part where we all struggle with, at least from a elected, or from the town's perspective, a city trying to issue permits when we know there's going to be a problem in a few years' time. Areas of improvement, the questions came back for making the data relatable and making it usable for the general public, keep adapting to new technology while maintaining what Hasim talked about, the connection to anecdotal local information. So that's those people that actually live there. And another area of improvement would be that there would be a phone app. Everything is app now, everything is phone now. If you want to know what's going on, you haul out your phone and Google it. And the thing has got to be on Google or on your phone. And then the millennials, the young people, they'll all do it. Those of us that are old, we won't. But nonetheless, thanks.
Thank you. You guys want to add some points if you have? No? Can we have next table?
Hi. So we have a representative here from Mount Pearl. So we also have a municipal perspective. And Mount Pearl has recently gotten their updated flood risk map and are very pleased with it. So that's good. She said the detail is just more than they were even expecting and makes it easier for them to implement changes. Although they're thinking, one thing that we thought about was that municipalities could use more specific guidance in terms of what to actually do with the information. Especially some smaller municipalities that may only have a couple people on staff. If there was sort of like a guidebook that they could look at and either like step by step how to work through some of your challenges or key areas, just something to kind of simplify the process might be useful. We also talked about communication between different departments in a town or even between the province and municipalities, because sometimes there could be, say, people dealing with the stormwater aspect and people who are dealing with the environment conservation river ecosystem aspect, and they may not be communicating so well. So those relationships could be strengthened. And so those are kind of the community needs aspect and some improvements. And overall, in terms of the technology that's being used and the depth at which the flood risk mapping is happening seems quite good. And from what I've heard from some of the people from outside of the province, it seems like we really are ahead of the game. So as long as we keep moving forward, I think we're on the right path.
Great, thank you. Next table.
You guys?
So I was voluntold as well. Yes, we for the community needs, we basically said yes, it's meeting the community needs. It provides a good baseline for the communities. But a comment was made by we have a representative here from Stephenville, so he made a comment that it seems that the FRMS evolves faster than the communities can handle. By that, we're having all kinds of rain events, and it's changing the rivers, and it's basically the communities can't afford to, sorry, a bit nervous, can't afford to keep up with the changing river systems. We, as for areas of improvement, we basically concentrate on what happens after the storm event. We talked about the erosion and stuff, but our discussion centered around depositions into the river systems. So you have a deposition that moves down the river during the river event, and the communities can't seem to get approvals to remove these depositions from regulatory bodies, and then subsequent events happen and moves the deposition even further or washes away completely, and they're left to be basically tied up in red tape in the regulatory process. So they were wondering if there's some way we could tie that into I guess some sort of streamlining of the system. And basically then you got your systems are based on the way that the river was before the event, and now your river has changed, and you need to update the model to account for that.
Great, thank you.
We have a winner.
Hello. So we have similar points to most of the other tables. Basically, we have a couple representatives from town of Cape Royal. So they said flood mapping in general, just to have it for their community because they do not have it yet, and just having this more accessible and funding for this. And they would like it broke down pretty simple, and so that it could be explained to also the general public of the town. They also think it would be good for people who do this flood mapping studies to come to the town and do small presentations for the public so that basically they can be more educated in this area. They also said basically like bank stability and infrastructure, if that could be a big part of the flood mapping, would be good. And what else? Also just like how communities are connected. So I know, for instance, like Mount Pearl got their flood mapping done, but they're also adjacent to Paradise and City of St. John's. And so those communities are tied together. So you need flood mapping for all of the communities around your area. So basically just all of the communities in general, because each one can affect the other. And I think that was most of it, yeah. Yeah, we're good.
Thank you. And our last table.
Anything to add, guys?
We said basically the same as everybody else has said, that the FRM can work or does work in municipalities that and areas that have proper enforcement and education for their councils, proper studies done. Improvement would likely be funding for the municipalities and for governments trying to mitigate the issues. And one thing I'll say from a municipal perspective, having a fixed line on a map is fantastic, but water is unpredictable. So if you tell somebody they can build up to a fixed line, how do you mitigate issues, 3 feet outside that line because the water flowed unexpectedly?
All right, thank you so much, all of you, for you raised so many good points, and they are all valuable to us, and we will take them into consideration. Thank you. Now we will move on to our lunch break, and we will resume at 1 p.m. Thank you.